Hello everyone, I'm Rekha Murthy, Assistant Professor from Department of Electrical and Electronics Engineering from Sai Vidya Institute of Technology. Today I'm here to continue with the next session. So wherein next session based on the module 2, wherein the topics are which we are going to discuss is the connections, the protective scheme which we are going to use with the impedance release. Next one, the connections of the impedance release and what are the different special cases are there for the zone 2 and zone 3 settings. And we are going to realize this impedance relay as an electromechanical relay and as well as the static and microprocessor relay. So let's move on with the protective scheme by using the impedance relays. See, as what we have discussed in the previous session, we are going to consider the three different zones. So there are 3 units of an impedance release which are required at a particular location for the 3 zones of protection. So it is a normal practice that we have to adjust the first unit to protect only up to 80 to 90% okay of the protected line. So in this case the protected zone of the first unit is called to be as a first zone of protection. Okay, first zone of protection. So it is a very high speed unit and also it is being used for the primary protection of the protected line. So this operation will be very instantaneous, about around 1 to 2 cycles. Okay, and this unit is not being set to protect the entire line to avoid the undesired tripping due to the overreach. So here, if the relay, if the relay is going to operate, if the relay is going to operate, if the relay operates for a fault which is beyond the protected line, okay, then that phenomenon is called to be as a overreach. So overreach may be occur due to the mainly transients during the fault conditions. So the main purpose of the second unit is mainly used to protect the rest part of the protected line, which is beyond the reach of the first unit. So the setting of the second unit is adjusted so that it operates the relay even for the arcing faults at the end of the line. So to achieve this unit, we must reach the beyond the end of the line. Okay, so here underreach is also caused by the intermediate by the intermediate current sources errors and errors in the data which is available for the initial setting of the relay, and also errors in the CT and VT and measurements performed by the relay. So to take into that account the underreach tendency caused by these factors, the normal practice is to set the second zone reach up to around 50%. So here from here to here it will be around 80 to 90%. The next here you can see there will be a partition, so it will be a 50% of it we have to leave apart, okay, for the first zone compared to your second zone. Okay, so here it will take into an account of second zone of up to 50% of the shortest adjoining line section. So the protective zone of the second unit is known as a second zone of protection. So second zone unit is going to operate after a certain time delay. So therefore its operating time is usually it is 0.2 seconds to 0.5 seconds. Next is the third zone of a protection. So the third zone of protection is provided. Will be the third zone. Third zone is provided for the backup protection for the adjoining line. So its reach should extend up beyond the end of the adjoining line, which is under the maximum under reach, which has been caused by the arcs, intermediate current sources, or the errors in the CT, VT, and measuring units, all that. So the protective zone of the third stage is known as a third zone of a protection. So this will be the third zone of a protection. Okay, so the setting of the third zone, it is going to cover what? It is going to cover the first line, that is the protected line plus the longest line of the second line plus the 25% of the third line. So the time delay for the third unit, it will be usually 0.4 seconds to 1 second. Okay, now this diagram, it is indicating about the stepped time distance characteristics. So here A1, A2 and A3, they are the A1, A2, A3, they are all the operating times for the zone 1, zone 2 and zone 3 release. Similarly, B1, B2, B3, they are also operating time for the zone 1, zone 2, zone 3 release, which is placed at a B. Okay, so because of the cost factors or the panel space, it is not possible to make use of all these three measuring units for the three zones of protection. So in a modern trend of the distance protective system, only one measuring unit is used for all the three zones of protection. Okay, so now the ohmic reach is usually increased by the timing unit in order to obtain the distance settings for the zone 2 and zone 3. So sometimes two units can be employed, one unit for the 1 and 2 zone and a separate unit for the third zone. So here distance setting for the zone 2 is done by the timing units. So this is about how exactly you're going to protect the fault with this scheme. So make sure here we are providing 80 to 90% and here it is 80% and here it is going to take up a small amount of 25%. Okay, so here now let's move on with the next part, that is the connections of the impedance release. So the same circuit what we had considered in the previous sessions, that we are going to look into after. So that circuit connections for consisting of the circuit breaker, trip coil, the contacts of a directional and impedance release, flags, timers, all that, which will be present here. Okay, and here Z1, Z2 and Z3, they represents the impedance release. And whereas T2, T2, T3, they are all contacts of the timer for the second and third zone respectively. Okay, for the second and third zone respectively. Next part of a circuit, also you can see that there is an improvement, but here in this case what you can observe that the characteristics which you are going to obtain, it will be for a different operating time like T1, T2, T3. Okay, so the characteristic circle for a Z1 is very small and the circle for the Z3 will be very large and the circle for the Z2 will be intermediate. So if any fault point which is lying within the circle Z1 and it is in the forward direction, the directional relay and all the three impedance relay will operate. Okay, so due to the operation of the first unit and directional relay, the circuit breaker trips in a very short period of a time of a T1. So a timer is energized whenever the directional unit and the Z3 operates. But after a certain definite time delay, you will find that the timer closes the contacts T2 first. And then after some more delay, the contact 3 will get closed. So the delays for T2 and T3, they are independently, they are adjustable. So if the fault point lies in the characteristic circle Z2 but outside the Z1, okay, if it is outside the Z1 and within the circle of a Z2, then the circuit breaker trips after the closure of the contacts T2 at a time of T2. So if the fault point lies within the characteristic circle of a Z3, but it is outside the circles of Z1 and Z2, then the circuit breaker trips after the closure of the contact T3 at a time T3. So whenever the relay is going to operate here, its flag is going to indicate its operation. Okay, and what is the purpose of the seal-in relay? Seal-in relay is mainly used to bypass the contacts of the main relay to save their costly and delicate contacts. Once the contacts of the main relay is energized and its contacts are closed. Okay, that means the current will pass through the trip coil. So the circuit breaker auxiliary switch is normally closed. So when the circuit breaker trips, so the auxiliary switch is open to prevent that unnecessary drainages of the battery. So if only one measuring unit is used, then the circuit connection can be modified like this. Okay, that is about the modified version of the diagram. So when the fault, the circuit is mainly depending upon to the what I had shared in the previous session about the impedance, the characteristics with the three zones that we have to take care and where the fault has been occurred and the uh, respective coils is getting energized with the respective times and the respective relay has to operate. So that we have to take into a consideration. Okay, so this completes about how the connections has been done. Next, let's move on with the what are the special cases are there with related with the zone 2 and the zone 3 settings. With the second zone or relaying units, we find that the transient overreach need not to be considered if the relays is going to have a very high ratio of reset to pickup, because any transients which is going to occur, it is mainly causing the overreach and it dies out before the second zone tripping time is going to get elapsed. So if the relay is going to have a very with a low ratio of a reset to pickup are used, then the zone 2 relay must be set to have a reach short enough so that its overreach does not go beyond the reach of the first zone relaying unit. So in other words, what you can say that the second zone reach, it must be short enough, which you are going to select with the second zone relaying unit of the adjoining line section, which is under maximum overreach conditions that you can see here. So in this diagram, this is what the second zone adjustment has been done with the additional time for the selectivity with with a relay of very short adjoining line, which you can see here. Earlier we had considered 80 to 90% of this, so now it has been increased further, and this was around a 50%. Again, you can see there is a small change, and for the it is covering up. It is almost covering up the entire two sections under the zone 1 itself. So this is how the zone 2 settings has been done. So zone 2 is totally is depending upon to the zone 1, which has been covered up entire region by the zone 1. Okay, so this is how you can avoid the overreach conditions. Okay, now to tackle this problem, the zone 2 delay time is made long enough to be selective with the zone 2 time of the adjoining line section. Similarly, this will be the third zone adjustment, wherein what they have done here is the third zone unit is provided for the backup protection for the adjoining line section. It should be set to reach beyond the end of the longest adjoining line section under the conditions of maximum underreach, which is going to arise mainly due to the arcs, intermediate current sources, and whatever the errors in the CT, PT, and measuring units. So in order to overcome this, this is achieved with the additional time delay, which you can see here, the third zone adjustment with an additional time, some more time has been taken up here, wherein we have not increased here. Instead of that, we have taken a little 50% of it at the initially, then later on we have taken a 50, then further we have covered in the entire region of the B. Okay, that is B1, B2, B3. So that will be the entire three zones has been covered under the one unit. Okay, so that is what has been completed in the zone 3 sessions. So the reach of any unit should not be so long as to cause the relay to operate under any load conditions, or it go to fail to reset if they have operated previously due to any kind of a reason. So we have to take care about both the concept, that is overreach and the underreach. Okay. So here what you can come to a conclusion is this is how the zone 2 and zone 3 affects to the zone 1. So, and how you are going to able to overcome the underreach and the overreach effects to either by increasing or either by decreasing the timings. Okay. Now let us go through about the next topic, that is how you're going to realize this impedance relay as an electromechanical relay. Now let me consider an induction cup type of construction, which I'm going to realize this impedance relay. So this construction is very simple and compact one, and it is going to provide a non-vibrating torque, and it is having a less affected by the DC transients, and it possesses a high speed and sensitivity. See, this is going to give you a perfect circular characteristic. See, in this case, you'll be having the two actuating quantities, that is V by I, should be less than or equal to K. That is what we had discussed in the earlier case. So in this case, for I into ZR is to be compared with the voltage if the amplitude comparator is used. But here in this induction cup type of construction, this is an phase comparator, and here we'll be having the addition of the two quantities and the difference of the two quantities, actuating quantities. So with the introduction of this, due to this ZR in the voltage circuit, so here the current flowing in this circuit will be V times of ZR. The current which is flowing through this circuit will be the V times of ZR. Okay. Therefore, we can say that, V divided by ZR. So here, therefore, the I plus V divided by ZR, I plus V divided by ZR, and I minus V divided by ZR. So these are the two quantities which you have to compare. So I plus V by ZR is the polarizing quantity, and I minus V by ZR is the operating quantity. So polarizing quantity produces one of the fluxes. So in case of the phase comparator, it provides the reference for the phase angle measurements. So this is what about the electromechanical relays, by which you are going to realize it as an impedance relay. Similarly, this is a condition which has to be satisfied at the finally. So let us see that how you're going to realize the impedance relay by using a static relay. So this static relay can work as a both amplitude comparator as well as a phase comparator. So let me consider the circuit. So wherein there will be a rectifier bridge comparator. So there will be a two bridge rectifiers. So this is mainly used to realize an impedance relay characteristics. So since here the amplitude comparator I is compared with the I is compared with the voltage V. Okay, so here this is the actuating quantities. I is compared with the voltage V. So I is an operating quantity, V is the restraining quantity. So as you know that bridge rectifier arrangement is a current comparator. So it is supplied with the operating current I naught. So it is supplied with the operating current I naught, and a restraining current means it is going to supply the restraining current IR. So I naught is proportional to that of the load current. So this I naught is going to flow like in this direction, and IR is it is also going to flow in this direction. So whenever you find that there is a difference in the flow of a current, immediately the relay has to operate. So I naught is proportional to the load current and IR is proportional to the system voltage. So this is what, whenever there is a difference in the current is going to flow, immediately this relay is going to react. This is about the static impedance relay using an amplitude comparator. Next, coming to when you're going to worry about its phase angle. So we have to think about its phase. So an impedance relay characteristic can also be realized by using a phase comparator. So let me consider your RX diagram what you had drawn in the previous session for an impedance relay. The radius of the circle is ZR, is considered as a ZR. Now let me consider this phasor diagram. So wherein here we are going to consider the current as a reference, and the product, when you're going to multiply this with the R, this is a IR. Okay, and similarly we have to, this will be the IR drop which will be in phase with the current I, as we all know it, and I into X is always leads the current by an angle of 90 degree. So if we divide all these phasor by the current, okay, see, finally you get that this is the current I, and IR is a voltage drop across a resistance which will be in phase, and I into X will be the voltage drop across a reactance which will be leading by an angle of 90 degree. Finally we get the value as a I into ZR. Okay, so in this case you will get value here. This value, what you're going to get, the amplitude is nothing but the difference between the I into ZR minus V. That is true. So that is the value of this line. Okay. Now what I'm going to do is, I'm going to divide all these phasors by the current I. Okay. So what does it results with? It results with only the RX diagram. Okay. This is what the RX diagram you will get. Okay. Now here you will get the value with all dividing by the current I. Okay. Now a circle with a radius of a ZR is drawn. Now you can draw the circle with the radius of ZR that you can see here. 1 minute. Yes, that you can see here. Okay, take a radius of this and draw a circle like this. So the point which is going to touch to the circle is indicating M. So Nm is the diameter of a circle. NO is the NO is equal to ZR. NO is the NO. Okay, so NO is nothing but, it will be equal, N with respect to a center O is nothing but ZR, and the phasor NP is this one. So you have to, what you need to do is take a opposite to this. Okay, that gives you minus ZR. So this you have to add up. So the value of the from here to here, it will be ZR plus Z. ZR plus Z, and when you take a difference between these two, ZR and ZR plus Z will give you ZR minus Z. Okay, I hope you are clear with this. So why this is a ZR plus Z? Because this is the value of minus ZR. Okay, and this is the Z. So when you take a difference between those two, it becomes Z minus of minus ZR. It will give you Z plus ZR. Okay. So you can see that here in this case, you can see that in this case, these are the different conditions which you can arrive. So that is I into ZR plus Z, I into ZR minus Z. We have to compare all these values such that this impedance relay can be realized by making use of a phase comparator. Okay. Now here also you can say that we need to compare with its value. For example, like if the point P, okay, if the point P, this is a point P, that is a fault point P, if it is going to lie within the circle, that is within less than theta, when the theta is going to lies within the circle, Okay, if it is less than the 90 degree. Okay, if the P falls outside the circle, then theta will be greater than 90 degree. Okay, now when the theta, when you see that if it is less than 90 degree, then the relay, when it is less than 90 degree, then you can say that the point is lying within the characteristic circle, that is I into ZR plus V, which is nothing but a polarizing unit. And I into ZR minus V is nothing but it is a operating unit. If it is outside the circle, then you cannot we cannot control that fault. It will come to the different other region. So this is what happens when the theta is lying within the region, within the circle, or when the theta is greater than 90 degree, what is going to happen. Okay, now next case, how you're going to realize this impedance relay by using a microprocessor. See, in the microprocessor based relay, what will happen is we are going to compare the two parameters, that is IRMS and VRMS. So there are number of techniques are there which can be used for this type of a computation. One of the technique is we have to use that IDC and VDC for the computation, as they are proportional to that of a IRMS and a VRMS. And also the another thing is VAC and IAC will be rectified by using a rectifiers circuit to obtain a VDC and IDC. So these rectifiers is going to make use of ICs and diodes. So now line impedance will be computed, and the microprocessor issues a trip signal to a circuit breaker if the fault point lies within its protected section. That is one method. Second method is that the microprocessor should take up samples of the voltage and current signals over certain like full cycle or a half cycle in order to compute what? In order to compute the VRMS and IRMS. Then the line impedance will be computed from these quantities, and again you have to identify if the fault point lies within the protected section, then a trip signal is issued. So after taking the samples, the microprocessor should make use of some digital filter techniques also to compute this R and X at the relay location, and take a decision to trip the circuit breaker if the fault point lies within the protected sections. Okay, now let's see that how you're going to modify this relay, impedance relay. How you're going to modify the characteristics of the impedance relay. This figure indicates the modified characteristic of the impedance relay. Its characteristic is almost a circle on the RX diagram. It is similar to that of an impedance relay, but what happens, it is been shifted. Okay, this has been shifted. Okay, it has a shifted characteristics. So to realize a modified impedance characteristic, the standard impedance characteristic will be shifted outside along with the RX axis via current bias. Okay, so this is this can be achieved by introducing an additional voltage into the voltage supply circuit of the relay. So that what will happen to the torque equation? The torque equation will result with T is equal to K1 into I square minus K2 into V plus IR whole square. Okay, so therefore, there what will happen, the modified impedance relay will have a greater tolerance for the fault resistance as compared to that of a impedance relay. Okay, this is how it will helpful also for the any kind of power surges. Okay, further when you're going to discuss in the next session about the power surges, definitely this modified relay will help out to overcome the power surges so that we can extend the fault for a long for a large value, okay, or for a more area of over a large region which you can cover up the fault. Okay, thank you for watching this video. So here finally we can come to one conclusion that what we have learned from this session is we came to know about what are the protective schemes which you are using in an impedance relays, and also what are the connections need to be done, and how you're going to improve the zone 2 and zone 3 settings. Then how do you realize the impedance relay as an electromechanical relay, And as well, we can come to know about how you're going to realize the impedance relay as a static relay as well as a microprocessor based relay, and also how you can modify the impedance relay. Okay, thank you for watching this video.